some more easy examples of U substitution, and of course, none of them are really easy, is this integral sec squared plus 1 divided by tan plus x dx. Now, one of the techniques that we can try is to try the denominator. So let's let the denominator equal u, equal tan x plus x. And the derivative of tangent, we know, is secant square x. We know the derivative of x is 1. And we know that this is going to be a dx. And the good news is that this is exactly what we want. Because if we look in the numerator, we have sec square x dx. And all of this will just become du. And the denominator is just going to become u. So what do we end up with? We end up with the integral of du over u. Or we can write that as the integral of 1 over u du. All right, now, a classical sort of thing happens here with students that's unfortunately incorrect, is they start this, they do u to the minus 1 du, and of course they try the power rule. And so that's going to be u to the 0 divided by 0 plus c, and that doesn't make any sense because we can't divide by 0. All right? And what did we do wrong? Well, we didn't do anything wrong algebraically. We just forgot that the derivative of ln is 1 over u, or ln u. So this is just going to be, for our antiderivative, this is going to be ln absolute value of u plus c. And then we can just back substitute for u. So this is going to be natural log of the absolute value of, remember, u is tan x plus our constant c. All right? And of course, if you want to check that, you just go through and take the derivative. One last, quote, easier example. Right? So we have this integral e to the x, fourth root of e to the x plus 178,000 dx. All right, so if you can't figure out how to evaluate an integral, maybe a u substitution with what's under the radical might work. So let's let u be equal to e to the x plus 178,000. And the derivative of that is just e to the x dx, an easy one. And the good news is that e to the x dx is right here. And that's just going to be our du. And then what's underneath is going to become u. All right, so what does this integral become? Well, it's going to become the fourth root of u, and then e to the x dx is going to be du. From here, we just write this as u to the 1/4 du, just like we were going for differentiation. And now we're going to find the antiderivative. Antiderivative just says we're going to add 1, divide by the new exponent. So u to the 5/4 over 5/4 plus c, multiply by the reciprocal, 4/5 u to the 5/4 plus c. And then finally, we're going to back substitute for u, which we said was e to the x plus 178,000. So one of two ways to write this answer. Actually, one of several ways, but 4/5 e to the x plus 178,000 to the 5/4 plus c, or if we wanted to write it back as a radical, we could write this as 4/5 fourth root of e to the x plus 178,000 to the 5th power. All right, so the numerator is going to be the exponent, the denominator is going to be your index, and plus c. All right, and of course you could take the derivative of that if you don't trust me, or you can just trust me and that can work for your answer. Every example that we've done so far, the derivative of the interior function has been perfect. In other words, if we look at the 4 examples, du works out to be whatever's on the outside perfectly. In this example, du sec square x plus 1 dx is exactly what we wanted, okay? But it doesn't always work like that. Sometimes we're off by a constant, and that's okay, right? We could still make it work. So in this one, we have integral of cos 2x. Now, if that was just integral of x, that'd be fine. One of the most common errors I see from students is they do this, sine of 2x plus c. And that is absolutely not correct, right? Because the error is not just, it's a cos of 2x, not a cos of x. All right, so this is a u sub. Let's let u be equal to 2x. The derivative of 2x is going to be 2 dx. Now, the good news is that we have dx. But what about this 2? Well, we don't have it, okay? But that's okay. What we're going to do is we're just going to divide both sides by 2. And so that means that du over 2 is going to be equal to dx. And that'll work very nicely because now we can substitute du over 2 right in for dx. And then we can just substitute u for 2x. So this is going to become the integral of cos of u. And instead of du, it's going to be du over 2. And we could factor out the 1/2. All right, so just pulling out this 2 right here, that's a half. And now this just becomes 1/2 sine of u plus c. And remember, u was 2x, so we're going to back substitute to finish this off. So we get 1/2 sine of 2x plus c. All right. Of course, if you don't trust me, you can go ahead and take the derivative. All right. And the 2, when you take the derivative by the chain rule, will cancel out with the 1/2. The constant will go away. So it looks pretty viable. Another easier example when you don't get exactly what you need on the outside, e to the 6x plus 2 dx. All right. So let's try the exponent. Right? There's nothing really else that it could be. The derivative of this is going to be 6 dx. And we don't want 6 dx, we just want dx. So just like we did in the previous example, what we're going to do is we're going to divide by 6 instead of 2 in the previous. So dx over 6 is going to be equal to dx. And now our integral in terms of u is going to be the integral of e to the u. And instead of dx, we're just going to substitute du over 6. We can factor out a 1/6. And this just becomes the easiest possible integral we have. So now we're going to get 1/6 e to the u plus our constant c. And then finally, we're going to back substitute. And by back substitution, we get 1/6 e to the 6x plus 2 plus our constant c. All right. So one last example. Right? And this one should be pretty straightforward. So we have x cubed minus 12. One of the tricks that we usually do is we try to take the derivative of what's in the radical. Okay, so the radicand. So we're going to let u be equal to x cubed minus 12. The derivative, 3x squared dx. And that's good because we want x squared and we want dx, but we don't want that 3. Right? So what we're going to do is we're just going to divide both sides by 3. And that means that du over 3 is going to be x squared dx. Now we're going to substitute for x cubed minus 12, and we're also going to substitute for x squared dx. So we're going to get the integral of the square root of u, and then instead of x squared dx, we're going to have du over 3. We've seen it twice already. We factor out the 1/3. Let's change u from square root to the 1/2 power. And now we can go through and finish this off. We're going to get 1/3 u to the 3/2 over 3/2 plus c. Right? Now we're going to be careful with our algebra here, right? Because we're going to have to do a little bit of work to be able to get to our answer. All right, so one thing you probably remember is that when you divide by a fraction, you multiply by the reciprocal. Right? And then we can just rewrite this as 2/9. And then I'm also going to substitute for u. Remember, u was x squared minus, or x cubed minus 12, excuse me. We still have the 3/2 power plus c. And now if you really wanted to, you can just rewrite this in terms of a radical. So our antiderivative is going to be 2/9 square root x cubed minus 12 to the 3rd power plus a constant c. All right, and again, you can check this by finding the derivative. All right, that's the really nice thing about these integrals is that you should be able to check your answers just by really quickly finding a derivative for this. Right. So we're going to take a look at a few more examples of indefinite integrals, and then we're going to start taking a look at these definite integrals. How do we evaluate those when we start having to do substitution?